Okay, so for problem chapter 439 exercises, we have a ball drawn from an urn of three white and three black balls, which sounds like one that we had done a couple chapters ago. But this time, after the ball is drawn, it gets put back in. So the difference here is that on every draw, we have a 0.5 probability of drawing a white or of drawing a black. That probability doesn't change. It's not dependent on the previous draws. So the question is, what is the probability that of the first four balls drawn, exactly two are white? So you can think of it as listing out white, white, black, black, white, black, white, black, 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 white, white. How many ways could you do that? Well, you'd have four different balls, and you want two of them, exactly two, to be white. So there's four, choose two different ways to arrange them in those four positions. And then each of those four, choose two, so each of those six ways that you could do that, you'd have a 1/2 chance of getting the first ball, 1/2, 1/2, 1/2. In other words, for example, let's look at black, black, white, white. You'd have a 1/2 of getting that first black, 1/2 of getting the second black, 1/2 of the first white, 1/2 of the second white. So 1/2 to the fourth. Notice also, of course, this is the binomial distribution that we're working with, and with a p-value of 1/2. Technically, they would write it typically as 1/2 to the second, 1/2 to the second, but in shorthand here they just wrote 1/2 to the fourth. And so that would give you a 3/8 chance that exactly two of the first four balls would be white. Okay, the next question was 51. And here's the first exercise that really deals with a Poisson distribution. Okay, and on this one, we're given that there's about 0.2 chance of getting a typographical error on a page. That's the expected value, the expected number of errors per page. Given that, they want to know the probability of the next page containing 0 or the next page containing 2 or more errors. So these questions where Poisson is used, they often feel like there's not enough information. All you know is the expected value, the expected number of errors per page is 0.2. That's all you know, and then you have to predict these other. They don't even tell you that it's a Poisson, so you have to recognize the situation where each page is fairly independent. And remember, if there's some weak dependence, that's okay, but in this case, this would make sense. The typo on one page probably wouldn't affect the probability of a typo on the next page necessarily. And we also know that it's a small chance. So we're looking for things with a large sample size, large N, so in this case, large number of letters or words per page, and a small probability of happening, a rare event. So in this case, P would certainly be small. Since we only have 0.2 errors per page of entire text. So this first one right here, the probability that it would contain 0, this is essentially just putting 0 into the PMF for the Poisson. So in other words, your lambda equals 0, or sorry, your k equals 0. Your lambda here would be 0.2. Lambda is the rate or the expected number of errors. Remember in a Poisson that the expected value and the variance are both equal to lambda also. That can help you in some of these problems. So on B, we have 2 or more errors. Essentially, we're taking 1 would be all the possibilities. So in other words, the k equals 0, k equals 1, k equals 2. Remember that the Poisson goes out to infinity. So that entire, if you would add those up, because it is a probability function, it should equal 1. But then we're subtracting out the chance that there's 0 errors, and we're subtracting out the chance that there's 1 error. So this would be the PMF for the Poisson with k equals 1. K equals 0, k equals 1. That will give us all the other values of k. So 2 up through infinity will be right there then. And finally, we have number 53. So we have 80,000 marriages in New York last year. Estimating the probability, part A, that on an arbitrary couple, both partners were born on April 30th. Well, if you think about what's the chance that a given person is born on April 30th, and again, this is assuming equal chance of having been born on any given date, which is slightly off, but it's a fair assumption. So that'd be 1 out of 365. The chance that that person's spouse would also be April 30th is 1 over 365. I think that's what I said the first time, hopefully. So 1 over 365 times 1 over 365 would give us 1 over 365 squared. So now, notice again, we jump to the assumption that this is approximately Poisson. So it doesn't specifically tell us, but we have a high n, 80,000, a low probability, regardless of if we're talking about one person or a couple, it's going to be a low value of p, and we're talking that there's roughly independence, equal chance. All of these things will allow us to assume that we're dealing with a Poisson distribution, or that we can at least approximate it fairly well with a Poisson. So how would we get the mean? Well, if we have 80,000 couples, and this is the probability that any given couple is both members of the couple are born on April 30th. So we have 80,000 times this probability. In other words, 80,000 divided by 365 squared to give us about 60% chance, 0.6 probability. This is the chance, let's see, what were we looking for? That both partners were born. So this would be for, so 0 is what we would want to plug into the PMF of the Poisson, and that's what this value is right here, because when we plug 0 in with this particular lambda, we're getting the probability that there would be 0 couples. So we want to subtract that away from the total probability to give us the probability that at least one pair were both born on April 30th. Now in part B, we're just looking for both partners had the same day of the year, not necessarily April 30th. So again, we can think of it in terms of maybe the male as our reference. So for a given male, what's the chance that his wife was born on the same day of the year as him? Well, whoever that male is, he has a birthday, so there's going to be 1 in 365 chance that the wife will have that same birthday. Again, assuming independence, equal chance here. So why is that different than this number up here? This one assumed a specific date. If we looked at April 30th, it still would be 1 over 365 squared. But this could have been any day of the year, so technically we would take this times 365, which would cancel out one of the 365s in the denominator, leaving us with this 1 out of 365. Or you can think of it as whatever the man's birthday was, there's a 1 in 365 chance that the woman would have that same birthday. Okay, so when we figure out the lambda of this Poisson, and again, 1 over 365 is still well below the cutoff for what we would say is a low probability. So in other words, we can still use the Poisson. This time our mean is going to be a lot higher because we're only going to divide by 365 instead of 365 squared. So instead of 0.6 for our lambda, we're going to get 219. And same idea here at the end. We're just going to plug 0 for k and 219.18 for lambda into the PMF for the Poisson, and subtract that away from the total probability, essentially this is going to give you 0.999999, so we're saying it's basically 1. In other words, we can be almost certain that of those 80,000 couples married in New York last year, almost certain that there was at least one where they were born on the same day.